Welcome to our third day and last day of Mark Hyman's mini course on sublinear time algorithms for approximating functions of many variables. So I wanted to, before starting, I just wanted to say we're going to have a group picture with whoever is in the classroom here. And if you're on Zoom, please be ready to show your video. We're going to take a picture with you, and at the TV here, there's a TV, and we'll send the picture via email. And also I wanted to say we're going to have, so you know, this event is being organized by the CRL Applied Math Laboratory. Tomorrow there will be a seminar by the CRL Applied Math Lab at McGill and also on Zoom. At the same time, the seminar will be by Professor Bruno Desprez on tidal neural networks from the viewpoint of numerical analysis. So we'll be there with Mark too, probably. So see you there if you want to join us at McGill tomorrow. And yeah, with that, I will give the floor to Mark for our last lecture.
Thanks. Yep. So this is going to be a change of topic a little bit and sort of general techniques from the last couple of days. So last few days we've been drilling down on the Fourier basis and whaling away there. Here we're going to use some different techniques that work for more general types of orthonormal product bases, and also I believe product bases even more generally than that, I suppose. And so this is going to be more about doing support identification, but instead of doing it using these combinatorial type methods, we're going to do it using collections of Monte Carlo integrations and using that to sort of inform a dimension incremental type of approach. So if you remember back to the first day, that was the second thing that I said we were going to talk about. So generally, we're going to have methods for more general product bases. That we're going to be talking about today, and probably the easiest references to give here are the very standard Trop, Nidell, CoSaMP paper from the compressive sensing literature going back a while. That's compressive sampling matching pursuit. This is from 2009. And the other sort of modifications of it that I'm going to start tossing in right away, more or less, can be found in a paper by Bosu Choi, myself, and Tony Volkmer. And it's going to be sparse harmonic transforms 2. From last year in Numerisch Mathematique, not pronounced correctly, I'm sure. All right, good. So let's start. I'm just gonna write down this a sort of generalized version of CoSaMP. Those of you who know CoSaMP should be not too surprised, and those of you who don't know CoSaMP will see what it's like. Because this is going to be very similar. So here is a generalized CoSaMP algorithm that we can discuss going forward. Okay, so let's take a look at what our input is going to look like for this guy. So I'm going to take some small set of measurements, again, compressive sensing type measurements for this algorithm, but I'm going to take two separate sets of measurements that I'm going to use for two different purposes. In the original paper, you took one and used them for both purposes. Here, we're just increasing the flexibility a little bit. So I'm going to take one set of measurements for coefficient estimation. So that's what CE stands for. And then it might be contaminated with arbitrary errors. This, just to remind you, is our S sparse vector that we want to try to recover using these measurements. This is going to be a matrix with, let's say, M sub CE rows. So we want this number of rows to be very small, right? So we have compressive measurements in general. And just like in the sort of original CoSaMP paper, more generally, this can contain any sort of extra junk that's added onto your measurements. So this is going to be some appropriately dimensioned vector that includes, for example, I'll put a little box around these things here, make it clear where they're supposed to belong. And this can include, for example, your measurement matrix applied to a vector that isn't actually sparse. So you can take everything that's not in the best S-term approximation to your original vector, and that could be some part of this. And you could also have other errors that are tossed in for other reasons and all sorts of stuff. So we should think about that. So we have this type of input. And very similarly, we'll have another set of measurements. This is support identification, support ID is what I'm going to sort of label these guys as. And same type of thing. So this will be an M by SID, an M sub SID by N matrix. All right, so just defining what the number of rows are, basically some notation here. Same sparse vector. I can toss on the same types of arbitrary errors, which could come from not actually being sparse, etc. Right? And so this is another input. Maybe I'll call it input A and input B. And then there are some other sort of implicit inputs you can take, like a maximum number of iterations, for example. Which I'll call kappa, some integer. So I can even say it's in cartoon N. All right, so we have this input to this method, and our output is going to be, hopefully, let's call it A. It's going to be a good approximation to, and I know I'm putting vector symbols on everything. I'm just going to not even try not to. You know who you are. Which is going to be a good approximation to the sparse vector. Okay, so that's what we're going to do here. So let's go ahead and sort of write down what this algorithm looks like. So first thing, we do some sort of obvious initialization. We initialize stuff. Start up here. So we'll start off with 0 as our approximation. I'm going to take the SID and I'll take my measurements here. Let me give these things a more concrete name, maybe. I'll call these the result of this. I'll call it YCE. Apologies. And I'll call these guys YSID. It'll be whatever these measurements turn out to be. All right, so I'm going to initialize this to be what I start out with my measurements. Not too surprising stuff here notationally. Whoops, that should be a Y. Yeah, perfect. And let me see, I want a number of my iteration. My iteration is going to start off at iteration 0. And then, so what am I going to do? I'm going to repeat something until a victory condition happens. And so what sort of thing should I do? I should integrate, iterate my current iteration. And next thing, line 4, this is the main difference from what you would generally do. I'm going to go ahead recover a subset of the larger support that I want to search for my sparse approximation, my good basis representation, for example, in. So I'm going to have a support identification algorithm that's going to take my support identification measurements, and it is going to output a subset of my total basis. So let's sort of make that more clear here. So this guy should be a subset of the power set of bracket n, right? That's where I'm looking for my basis. And in particular, I'm going to say that this thing should have cardinality at most 2s for my sparsity parameter s. And the idea is that we would like this to be approximately equal to the support of our true sparse vector that we're trying to recover, right? So that's what you should think about this magic function of doing. So it's taking a vector in C M sub SID, some vector measurements, and it's shooting out some hopefully decent support set. So the main sort of difference here. And then what do? The rest is completely just regular CoSaMP. So you go ahead and take this newly useful omega tilde set you just discovered. You take a union with that and the support of your last approximation, whatever it is. From the last iteration, you go ahead and truncate your coefficient estimate matrix. So phi prime, this will just be 1 over the square root of MCE times your coefficient estimate matrix, which we're assuming we also know restricted to this new support set. So this means take the columns that are indexed by omega. I think we've used this notation before. And this is going to be just for reference, this guy is going to be a matrix that is at most MCE by 3s. It might even have fewer than 3s elements, I guess, but that's the most it'll have. So this is going to be, the point is this guy should be S sparse. So this is going to be size S. This thing is 2s. So we have some bound on how big this can be, and it's relatively small. All right. We're then going to solve the least squares problem to learn coefficients on this good support set. So I'll call that B. On the support set, we can solve the least squares problem from, that's supposed to be pseudo inverse Y CE, I guess it should be BCE, divided by the square root of MCE. I believe I didn't mess up my normalization. And then what do? You go ahead and use these coefficients on omega to update your next iteration. So we'll go ahead and set our new best S-term approximation to be B restricted to omega, and then I'll take the S largest one, so it's S sparse. And right, okay, I didn't have to do that, but I'm doing it anyways. Great. So we're almost done here. We update all of our samples by subtracting off from our initial samples the contribution that we just estimated, right? So we have all of this stuff, and now we have to update all of these samples instead of just the one set of samples. So we do our new BCE is going to get our initial measurements, YCE minus the contribution from phi CE applied to our sparse approximation AK, which should be AJ, sorry. And same for the SID measurements. So this just says same for SID. Right, we update all of our samples or both sets of samples. And then what now we repeat this until we exceed our coefficient, our sort of number of iterations that we put in for our limit. Or if you want, you can do this until your remaining coefficient energy increases from last iteration, if you want. In other words, you made some kind of mistake in discovering support or screwed something up, so you're sort of stalling out on making progress on decreasing your coefficient error, right? Because this thing now contains what's left over, so it should be declining. It should be a monotonically decreasing function, so you can sort of cut it off. It starts increasing and doing weird stuff. And then, right, when you're doing that, when you're finally finished, you go ahead and return your current iteration. Or if your coefficients increased last time, you return the last one, the last iteration where the error seemed to be smallest, right? You sort of do this. Okay. So this is effectively exactly CoSaMP from the Trop and Needell paper. And I want to point out that it is an algorithm that is incredibly fast if this fourth line can be done quickly, right? All of the computational complexity can more or less be described in the following way. So just looking at this thing, maybe I'll wish I had, I do. So the runtime of this thing. This is a convenient place to put it. It's more or less going to be the maximum of the runtime of whatever this support identification algorithm is, right? And otherwise, the time to solve least squares problem, that's relatively small. So of size MCE by 3S. Right? And this is going to be, for those of you who know what I'll talk about next, an RIP sort of bounded matrix in general. So this is going to be on the order of S log n or something like that, maybe powers of log n, right? So very small. You can do this pretty fast. Sublinear time. This is a sublinear time operation. So if I can just figure out how to make a reasonably accurate and fast support identification algorithm, CoSaMP becomes a sublinear time algorithm. Right? That's what I want to convince you of at this moment. Good. Any questions about this CoSaMP stuff before I sort of drill down onto what this algorithm, the support identification algorithm, should maybe do?
Mark, more of a comment than a question. The runtime will also depend on the maximum number of iterations, right? Which presumably is also going to be small, right?
Okay, yeah. So that is also true. Kappa times this. Kappa is usually going to be like a few hundred or something at most, probably. Yes, but you're correct.
The second line in the runtime, like the maximum, the time to solve a system of that size?
Yeah. So this is a matrix that you want to solve the least squares system with respect to for some vector of coefficients. Of size 3s in particular, I guess. Right? So. Perfect. Yep. Any other questions? Okay, good. So let's talk a little bit more then about.
Mark, sorry, just one came
Yes.
to mind. So the step 9, the stopping criterion. Why? So VC. Okay. Or yes, but the support identification doesn't matter, or like they will behave the same way. So, like, I mean, why is the subbing criteria only involves the coefficient estimate?
You could put the support identification in
Okay.
there too. It's just that this is, it turns out in what we're gonna see next, that this is more obviously like just an RIP matrix type estimate. And so it's easier given existing results to say when this starts increasing, then you have an error bound that you've maxed out in terms of a best term approximation, and so you can quit. But yeah,
Okay,
but you're completely correct that actually given that the number of measurements you're going to use for support identification is bigger, it's probably better to even say that that should be decreasing. But it's also not going to be just an RIP matrix. It's going to be a strange union of a bunch of weird sampling sets that are harder to analyze. So this is just for theoretical convenience.
okay,
In practice, you would probably use both, yeah,
I see.
or possibly even just the other one. But yeah. Yep, that's a good question. Other things that folks might be interested in? All right, so two questions then that may occur to you. So the first one is, I want this entire CoSaMP algorithm to be accurate. What does this have to satisfy in order to guarantee that it'll still be accurate, right? So it's the accuracy question. And then the speed question, how do I make something that has that property that's still fast, right? So let's do accuracy first and talk about what we need in order for this to actually guarantee that CoSaMP still works. All right, and we'll work there for a while. All right, so first question to think about here. What does this weird function have to do that takes these measurements and spits out some small and cardinality power set of the basis so that CoSaMP is still accurate, meaning it still has best term approximation guarantees of the type you actually want. My spelling of accurate is probably very inaccurate, but whatever. All right. Good. So I will give a general condition for this. It's going to look a little bit confusing, so prepare yourself for parameter purgatory. And then I'll give examples and you'll see what it means and why it sort of makes some sense, some easy and less easy examples. So here's a definition of what you need in order to ensure that CoSaMP will still work. Okay, so good. So we choose our sparsity, right? And I'm going to choose another parameter beta that we'll see in a second. I have to talk about the measurements I'm going to feed into this guy. So I have to talk about this SID matrix as well. So I'll say it's M by N, so I don't have to put SID everywhere in this definition at least, right? So we have some matrix which is going to give us measurements, and we have our algorithm exactly of this type, except I'll remove the SID so I don't have to talk about it so much. It outputs some set of indices that should hopefully be a good support set. And perhaps most annoyingly, I'm going to have some other function from vectors of this size. This is going to handle additive errors and sort of tell me, so what does this do? I can tell you what it does, I guess. That's usually good when you're trying to tell people stuff to tell them stuff. This is going to tell us effectively when additive errors on the measurements cripple your support identification algorithm and make it inaccurate. So that's sort of what this gamma is going to do. So you can think of that for now, and then we'll see how it does that. So it's just going to output some positive real number. And generally, so that we don't have stupid things happen, we're just going to say, you don't have to do anything with this function except have 0 mapped to 0. Right, so that's going to be, in other words, if you don't have any noise, then you should never be crippled with your algorithm. So it sort of makes sense if you think about it that way. Okay, so here's the actual definition. So there's going to be a triple of the matrix, which I guess I also might as well remove this from SID from, because I removed it from everywhere else. Okay, it's going to be a matrix algorithm in gamma. So I'll say this triple has the support identification property. Or if you like, SIP, because why not, of order S beta. So our sparsity and beta parameter come in if the following is true. So we want any vector when supported to, or when restricted in support to the output of this algorithm based on measurements of the vector plus additive error. Okay. And in 2 norm. So this is a restriction of this vector, right? Based on input measurements. This is what this thing puts out as a set. We restrict to that set. We want this to be less than beta times the total 2 norm of V. And we want this to hold, I see I've made a strategic error in my board placement. That's fine. So we want this to hold for all sparse vectors V. So B should be S sparse, as you might expect. That's where that parameter comes in. And for all additive errors that you can add on to your measurements, with the property that the 2 norm of V is greater than this gamma function applied to the error vector. Okay. So let's sort of go through this again, right? So we have this, ooh, and it gets a little bit worse. I actually want the complement of this set. Dang. That would have made a big issue later. So I want the complement of this set. The stuff you don't discover, sorry, should be less than beta times the norm. Okay, so, right, the stuff you miss. If you like it the other way, let's point out that this should be equivalent to saying that 1 over beta squared minus 1 times V restricted to the complements of the stuff you miss. Should be less than the stuff you find. So it should be less than V restricted to the stuff you actually did find. Okay, in 2 norm. All right, so point is you want to find a lot of the energy, right? So that's what that means. But it doesn't have to always work. It only has to work for S sparse vectors whose norms are big enough. If your norms get small enough that you sort of no longer exceed whatever this gamma function is, it sort of tells you when your algorithm breaks, then you no longer have to satisfy this. So this builds an error floor into this sort of triple. This sort of tells you you have to be able to find support as long as your error isn't any bigger than this for anything that's S sparse. And that's sort of what it means. Okay, hopefully that is slightly clearer than mud. Okay. And if it is, we can sort of look at some simple examples of things that work that give you these SIP triples. And then, so after doing that, I'll give a theorem that tells you how well CoSaMP is guaranteed to work in terms of these SIP triple definitions. So we'll be coming up a more detailed statement telling you exactly how well CoSaMP is going to work depending on what this triple looks like. Okay. Good. All right, so let's see maybe the easiest possible example of one of these things. Just to demonstrate that they certainly can exist, at least if you do things that are algorithmically useless. All right, so let's say that my matrix is just the identity. So in other words, this is particularly dumb because I'm not compressing anything, but okay, I can do that if I want. My sparsity can be any even number. Let me take beta to be 1/2, right? And my support identification algorithm, which is going to take identity times V, so just V here, right, is going to be equal to the support of V restricted to S divided by 2. So this is sort of telling you that if you find some of the support, you can be one of these things, right? So this is like, you just need to find some of the support. That's the point of this example, really. And you'll satisfy this. And I need a gamma, so let me do a dumb gamma that says, let's only worry about the noiseless case. So my gamma can be equal to 0 if E is equal to 0, because I have to do that. And I'll just, for everything else, I'll map it to infinity. And what does that mean? That means as soon as it's not exactly sparse, you're allowed to break, right? So, but still, you can do that. All right, so this thing, which only finds half of the support, just sort of getting that across here, find in this way, has the support identification property of order S 1 over the square root of 2. So S beta for that particular beta. Okay, so, and the proof is pretty easy, so we might as well go through it. Maybe the notation will make some of this terrible definition a little bit clearer. So let's think about this. So if I take my vector and I restrict to the complement of the set output by this guy, and look at its 2 norm. So this is going to output the best S over 2 approximation to V, right? So that means that this is going to be exactly the 2 norm of V minus VS over 2. Right? And so what we want to know is this, so I'm not asserting that this is true, but we want, in order for this to have the SIP triple property, is this less than 1/2 over the square root of 2 for times the 2 norm of V for all S sparse V? And we don't have to worry about errors because our gamma is like trivial, so errors have been thrown out already. Okay. All right, and so the answer is going to be yes. So if I take my S non-zero entries of B and I go ahead and order them, so the J first entry is bigger than the J sub 2th entry, etc. So define things this way. Then this is only going to hold. So this is the definition here. I'm going to use this. So star, what I want to verify is going to be equivalent to verifying that the sum, so I can square both sides of that, and then I'm just adding up squares. I'm going to have that this error is going to be, because it's S sparse, the S over 2 plus first one, adding up to S of these guys. So that's going to be exactly the same as saying that this is less than 1/2 times the total 2 norm squared of that thing. So 1/2 squared times the 2 norm squared, which is going to be L equal 1 to S to L. And now we rearrange. Let's subtract this side from this side and rearrange a little bit. And you basically see right away that this is going to work out in your favor, because if I subtract the half of the smallest ones from this side, I'm going to get that this is equivalent to having 1/2 of the sum of the smallest S over 2 things being less than 1/2 of the sum of the largest S over 2 things, and that's clearly going to be true. Right, so that works. So there's a sort of dumb example of something that works. All right, so point of this example, besides maybe making the definition look a little bit clearer, is that, and just like in CoSaMP, still with this sort of definition, we only need to find a subset, so a few of the most energetic entries each time to be a SIP triple. Right, so this really is sort of doing what you expect it to do through this sort of obscure definition. All right. Any questions?
Yeah, in
Yep.
the previous group, why did you need the last step? Weren't you okay in the second last step?
I guess just to make it easier, like if I take the S over 2 plus 1, the S guys, and subtract them from these, then this just, I think, makes it really
Oh,
clear.
yeah, because
The last ones are going to sum to something less than the first ones, and there are just as many of both of them, and they dominate. You know, the first ones dominate, so it's always going to work. Yes, good question. Any other questions before we see a less trivial example? So that actually uses compressed measurements. Right, so it would be nice if the original CoSaMP paper used the SIP triple, right? That would be good, and it did. So another example is the following SIP triple, which is implicitly in the CoSaMP paper. So this is example 2, and it's less trivial because it actually involves compression. Okay, so here we want our matrix to have the RIP property. So these are going to give us our measurements for our support identification method. which turns out to be identical to the matrix you use for coefficient estimation, but it doesn't really matter, right? So you can use them for support identification as well. So these have the restricted isometry property, or this matrix has a restricted isometry property. And I can remind folks what that means in a second. So of order 2s, and they give a particular beta 0, 1. Turns out to be the beta. Okay, so all right, well, so let's remind ourselves what the RIP property is. I might as well make sure that for the students in the house I define it. So this is some epsilon. It should be some value less between 0 and 1. In this case, it happens to be 0.1. But if this is epsilon, the RIP of order 2s epsilon is, so what does that mean? That means that you should approximately preserve the norms of all S sparse vectors, all 2s sparse vectors in this case. Right. So if I take this matrix and multiply it by something that's 2s sparse in this case, it should approximately preserve all of the 2 norms up to distortions on the bottom of 1 minus epsilon, which in this particular case is equal to 2, 0.1 and 1 plus epsilon. So between 0.9 and 1.1, right? And this should work for all vectors x, which is the hard part, with sparsity less than, so this is the L0 norm less than 2s. So that's what the RIP, this is what the RIP property of this order means, right? Just so that I know I've said it. Okay. So this is the matrix. It's going to have this compressive sensing property that we know how to get from a multitude of sort of sources. You can look in Simon Ukar and Holger Raudgut's book, for example, or anywhere else you like to look for compressive sensing things. We also need an algorithm, and we also need a gamma. So what are their algorithms? What's their script A, their support identification algorithm, and what is their gamma? So all right, so their A in this case, which is going to output some weird set, is the following. So what do? We are going to take the support of the conjugate transpose of our RIP matrix multiplied against B. So this is what alpha B is going to be. I'm going to take this conjugate transpose of this matrix. This is going to be something of size n. I'm going to take the largest S entries of this thing, and then I'm going to output them by outputting the support of that sparse vector. So that is my map that maps measurements to a set. And so that's my second piece. That's what the original CoSaMP algorithm has in line 4 instead of effectively what is there. And their analysis, what gamma turns out to be, it's the following. So I take my error in, and what I have to output in order to get things to work with this definition is going to be 2.34 over beta minus 0.2223. And if you look in your paper and find those constants, you'll see exactly why it has to be that way, times the 2 norm of E. So that is my map from E to the positive numbers, and this, we just have to put some kind of support constraint or some kind of constraint on beta so that we don't divide by things that aren't nice. So we can put beta in that interval. Okay. And so we have a little lemma that you can prove without, if you look at their paper. So I'll say this is implicit in the CoSaMP, the original CoSaMP paper. And it says effectively this triple, the example 2 triple, is a SIP triple of order S beta. And it's a reasonably efficient SIP triple. So, so its runtime is going to be what? It's going to be the order of the maximum time it takes to, at worst, sort the support so that you can find the S biggest things. So n log n sorting time, and the time it takes to apply the conjugate transpose of this matrix, whatever it is, to a vector. So it's not sublinear, but it's reasonably efficient, right? And that was the whole charm of CoSaMP, basically, or one of the charms of CoSaMP, I should say. Okay. All right. So the original result had this property. So here's a theorem I'll finally give you that tells you an error bound for CoSaMP, the algorithm that I actually wrote out, if any time you have a triple like this. Yep.
Could you please explain what the algorithm here is again? I don't quite understand.
Oh, yes, this algorithm. So I multiply the conjugate transpose of this matrix. So this matrix is m by n. So this is going to be an n by m guy that I multiply by my vector. And in this case, remember this is in cm, for the size of this thing. All right, so then I'm going to find the largest entries of that vector. And I'm going to zero out everything. And then the support says just return the entries where those non-zero entries are.
Okay.
So really, I just want to find the entries of this vector that have the largest magnitudes. What I'm doing.
It sounds like a threshold.
Yeah, it's a thresholding step, exactly. And that's all. That's all that's going on. This is just a sort of easy way to write that, assuming that you remember all of my bad notation. Yeah, good, excellent question. Other questions about stuff? All right, if not,
So yeah, Mark, yes. So just a curiosity about the numerical values of the constant.
oh, these things.
Yeah, like I guess you kind of fixing a probability of failure or something, and then you
Oh,
get these
these are
constants.
pulled out of the error analysis that they have in the CoSaMP paper.
Okay.
So these are just numerical constants that they ended up with in their analysis of the original CoSaMP recovery theorem.
Okay, but they depend on the RIP constant in principle, I guess.
They're going to depend on the RIP constant and this 0.1 being 0.1 in particular and stuff like that. Yeah.
And there's also some dependence on the probability of failure that they're fixing, or that. is not-
That I don't think appears. They just assume that this thing has the RIP and then go.
Ah, okay, right. We're even before that, right,
Yep.
okay.
Very good. So this theorem just gives you the freedom to do your own SIP triple and still know that CoSaMP is going to work. So what does it say? Ooh, well, maybe I should have saved the definition, but it's gone now. All right, so this is a theorem of my graduate student Bo Soo Choi and Tony Volker and I. It just says the following. So what do we want? So if in the algorithm that we wrote out before, which has long since been erased, so we have these measurements which were support identification. I had potentially a different support identification matrix. And I had potentially a different set of measurements I was going to use for coefficient estimation. All right, so with these as input, so if they have the following property, so what do we need? We need something nice from the coefficient estimation matrix, and it's that it should be an RIP matrix still. So this guy, this coefficient estimation matrix, after we renormalize it properly, has the restricted isometry property, so it preserves the norms approximately of all 2S sparse vectors, just like before, up to delta, which is going to be our error, could be 0.1, for example. And what else do we need? We need that our support identification algorithm and the associated measurements we use for it so this should just be a SIP triple of order 2S beta. And so we saw one sort of dumb way and one nice way from the original paper of how that works. Then the CoSaMP algorithm that we wrote out before termination conditions that we had will have an output A that satisfies the following guarantee. So XS minus the approximation A that is output from this thing is going to be less than the maximum of I'll put explicit constants down because you can get them. 1.03 gamma ESID. So whatever this thing is, plus 2.03, it's kind of pointless to write it out, but I'll do it anyways. Coefficient estimation divided by the square root of MCE. So this is one possible error bound that you have. And the other one is e to the minus kappa. That was the number of iterations you're going to do times the 2 norm of XS plus 9 times this same ratio of the error you have on your coefficient estimation measurements. Okay. So the maximum of these two things. And where do these come from? Well, this is my number of iterations is high enough that I iterate until I don't make any more progress. Basically, I iterate until my support identification algorithm breaks, and I start outputting garbage for my support, right? And I notice because my VCE will go up at that point, I quit. And then wherever I can't make any more progress doing support identification will be the cutoff, and I'll have an error there, right? Plus my my coefficient estimation on whatever that good support was, where I sort of crapped out and couldn't make progress finding more good support elements. And on this side, my number of iterations was too small, and I just kept making exponential progress and then gave up before my support identification failed. So whichever one of those is bigger is my error guarantee. Right. So this is always going to work. And the maybe most interesting thing about this is that CoSaMP triples like this. So this is still part of the results from this paper, effectively. So CoSaMP triples of this kind. The other thing we wanted besides accuracy, which this tells us we have, as long as we have the support identification property, is a sublinear runtime. Right? So we want to know how fast can we actually get something that does this. So we can say that CoSaMP triples with runtimes like I'm going to suppress a whole bunch of constant factors and log factors and things like that here. So that scale, like the sparsity to the 5th times or plus the sparsity cubed times n, something like this, exist. When these guys, these two matrices are bounded orthonormal sampling matrices. So come from our particular type of restricted isometry property matrix that is of interest in function approximation applications. But in general, well, yeah. So nonetheless, they exist. All right. So sort of some in the worst case, some somewhat punishing dependence on sparsity. But again, if and let me see. And let me, and this n is misleading. So this is the total basis size in my example was n. So let me make this clearer. So maybe it'll be more correct to say, yeah, that's a notational issue. The n there should be like the dth root of n, where the basis size is some number of orthogonal polynomials in each dimension, and you have d dimensions. So you have n to the d as your total basis size. So in that sort of situation, it's like a dth root of the overall basis size. So maybe I'll put this here. All right, so in other words, it's sublinear. So that shouldn't be at the n, which is the total basis size. This is something smaller than the total basis size. So there are sublinear time support identification algorithms. Okay, that's probably enough damage for this hour. Any questions about this stuff? I can probably quit and come back with the rest next time. Yes.
So about the gamma function, so like this whole time we've been talking about like all of this is like robust in the face of noise as long as the noise like isn't too big. So is like the role of this gamma to quantify exactly what we mean by too big?
It quantifies by what we mean by too big. It sort of tells us in some sense how robust the support identification algorithm is. Okay. That's what its job is in our error analysis. Yep, excellent question. Any other questions before I do, or we do our whatever minute, 10 minute, 15 minute, 15 minute break? Okay.
Good, yeah, so yeah, great. Maybe let me say, stop the recording, but let me say people